Ladies and gentlemen, we're going to talk today about the rapid prototype, or some people know it as 3D printing. 3D printing of materials. Now, we did several projects on 3D printing of polymers, ABS, acrylo, butadiene, styrene, and we're doing now another project on an acid. What is it called? What kind of acid? Lactic acid? Anyway.
Yeah, PLA, yeah.
Yeah, we were doing work also on another polymer. Now, 3D printing is a very, very important concept because you can produce the whole part without having to do machining and wasting material and doing extra steps. I mean, you can do the whole product with just printing the material layer by layer by layer. We are doing one of the projects on 3D printing of aluminum. And we're going to also do other projects on 3D printing of titanium and of nickel. But we're going to talk today about the rapid prototype behavior of 3D printing of polymers. I'm going to give you a paper that we did several years back. It is very highly cited. And Mr. Jiadong Sam is going to give you an experiment on ISO testing or impact testing of polymers. What we're going to concentrate on is the effect of the way that the layers are oriented on the 3D printed materials. So for example, let's say that I would like to produce a tension test. So I want to produce a tension testing I want to test by tension rapid prototype samples. Now, if my sample looks like this, I can print the sample such that they are parallel to the length of the sample. Or I can print them in a way, like many companies do, at plus minus 45 degrees. Or I can produce the samples at, which is a bad way, by the way, I can produce the samples at a layer orientation of 90 degrees to the length of the samples. So we're going to call this as 0 degree, meaning it is parallel to the length. This as plus minus 45 degree to the length, and this is at a 90 degree to the length. Like in composites, if you produce a sample this way versus especially this way, it will be, this one will be stronger and more ductile. And this one will be weaker and less ductile. And because we don't know where are the stresses coming from, we produce this type, which is, let's say, medium strength and medium ductility. You know, we're trying to take the, to solve the problem that we don't know how the stresses, the combined stresses are coming from. Now, what I'm going to do is talk about 3 tests: tension, bending, and isol. Now, I'm going to show you two samples. This is a sample. This is a sample which was at zero orientation, and it broke by breaking layer after layer after layer. And this one is a 90-degree sample which broke very fast, perpendicular to the length. What happened? What happened, guys, is that when you broke the sample in tension, so I applied tension here, what will happen is the crack had to break this layer, and 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 that's why the material is strong. On the other hand, the crack just went in between. So here is layer after layer, and here in between, again, as you see, the crack had to go and break the sample layer after layer after layer after layer after layer, like here, while the other one very, very easy path and just broke the sample in between the layers. Accordingly, it is much better to produce your samples this way than this way. Now, when you do a 45-degree, you're going to find that the breakage is going to be much slower than the 90, but not as good as the 0. But this one is optimization. Optimization, like if you put a composite on an aircraft, you don't know the stresses, where are they coming from. If they're all coming and you know one certain way, you can produce your fiber this way. But when they are coming all over the place, this is your safeguard. So we spoke about the tension test. Let me talk about the bending test. In the bending test, I'm going to have a force, and I'm going to have two simple supports. This is what we call 3-point bending. Like you have 1, 2, 3. And what will happen is your sample is going to be deformed such that here you have compression and here you have tension. But when you have the sample, so let me take the sample, and the layers are parallel to the length, which is 0, versus the sample when the layers are perpendicular to the length, which is your 90. You're going to find that here the crack is just going to go nicely in between, no problem. But here, he has to break this, and this, and this, and this, and this. And that's why bending here, which we call sigma bending, some people like to call it modulus of rupture. I'm going to give you the publication, and you're going to see this in more details. And this is usually equals to 3/2 F where this is the force F, times L divided by, I think, the thickness squared times the depth. So if I take here the thickness, and this is the depth or the width, we'll have a formula like this. I'm not sure if it is correct. We can check it out later. I'm not very good in memorizing formulas, but it's something like that. So again, in bending, the zero is much better. Take a look at the following. This is 90 degree. When you bend it, it broke in a second. While this is the 0 degree. And as you see, you have to go through one by one of these so that you break the sample. Now, I want to go through the last test, which Mr. Jadongsan will do for us. Hopefully we can do some stuff in person, but if things keep on this way, we will just have to have Mr. Sun do it for us, and we will look at it and talk about it in the lecture. Now, if I have a sample and I have a hammer, and I have here an H node, which is initial height. And if this sample is released and it comes here, and it breaks the sample, and it swings back here. And this is my HF, or the final height. Now, the energy absorbed, which we think of it as ductility. Remember, guys, the word ductility, from the first test, which is the tension test, we said ductility is percent elongation in a sample, which is final length minus initial length divided by the initial length times 100%. So this is length, this is initial, and this is final. And we said it is percent reduction in area if you are doing a cylindrical bar. And this is A0 minus AF divided by A0. The same 0 and F have the same notation, but this is the area. Now, other things which mean ductility is the ISOD or impact test. In fact, when you become seniors, if you do your master's here, or if you take with me a 500 level course of fracture mechanics, I'm going to give you another term called fracture toughness, which is a test of that. So, the energy absorbed, or the ductility, is proportional to HF minus H naught. What does that mean? Let me first erase the board and We're going to talk about this in a second. I'm sorry, it should be H naught minus HF. So, if the sample is brittle, then this guy is going to break the sample and keep on going high. So let us say that this is 5 and this is 3 or even 4. So 5 minus 4 is going to give you 1, which means it's very brittle. On the other hand, if the hammer comes toward the sample and the sample sucks the energy and the H naught, the HF, so this is HF1 for a brittle material and this is HF2 for a ductile material. Then for the ductile material, I'm going to have the same constant, which is 5 minus 1, which will give you 4 units of energy. So this is for brittle, and this is for ductile. So for a ductile material, the hammer will not have the freedom to go up all the way to here. It will only go up to here, because this thing has